Now that we have defined expectation for a discrete random variable, let us look at a formal example. Let's have a look at example 1. And the example will go like this. Suppose a vending machine dispenses a random number of candies when a button is pressed. Let x, or I guess the random variable x, representing the number of candies has the following probability distribution function. Has the following probability mass function, I'll just say. And let's give it here. Let's say it's p x and the probability x equals x. We've got 1, it takes the values 1, 2, 3, 4, and 5. And let's say they occur with probability 0.1, 0.2, 0.4, 0.2, and 0.1 respectively. Okay. And our question is to find the expected value of x. All right. Well, in this example here, we can take a look at the solution to this problem. And very easily, we're going to use the definition that we derived in part 1. And that's to say that the expected value of x is equal to the probability density or the sum of x times the probability mass function, I should say, and we're summing across all values in the support of x. So in this particular instance, that becomes 1 times the probability x equals 1 plus 2 times the probability x equals 2 plus 3 times the probability x equals 3 plus 4 times the probability x equals 4 and plus 5 times the probability, x equals 5. Substituting in the values that we have from our probability mass function above, we get that becomes 1 times 0.1 plus 2 times 0.2 plus 3 times 0.4 plus 4 times 0.2 plus 5 times 0.1. And after all of that, we get 3. And perhaps there's some logic to this as well, that we do get an answer of 3, because if you look at the distribution here, it's actually equally weighted. That 1 is equally weighted with 5, 2 is equally weighted with 4, and so we're sort of getting to this average or the central tendency that 3 is sort of the middle number and also in the middle, which sort of makes sense. Now I'm going to posit the following conclusion, and then I'm going to prove it. So suppose that the random variable x, so we're going to look at a more general case now, not looking at the example, but suppose that x has support, and we'll say 0, 1, 2, and forever, effectively. What I'm going to suggest here today, that this suggests we can compute the expected value of x from simply the probability or the cumulative distribution function, which is defined as the probability x is less than or equal to x. This is my belief, or this is what I'm going to set out to prove to you today. And the only condition that needs to really hold is that the support of x is as non-negative integers. So let's do that now. Let us prove this below. So, firstly, looking at the original definition that we came up with as the expected value of x. This is equal to, well, it's the sum of x's across the support of x times px of x. Now, I've already suggested to you here that the support of e of x, that the support here that I had before is from 0 to infinity. So I can substitute that in the summation immediately. I can say that is x equals 0 to infinity of x times px of x. The next thing I want us to note is that for the very first terminal, right, so for the very first value of x that occurs, x equals 0, well, that first term, 0 times probability x equals 0, well, it cancels out, in fact. So I can actually just start my summation at 1, quite frankly, because the first term will simply collapse to 0. Now I'm going to write this, or I'm going to expand it out for us. So that will be 1 times px of 1 plus 2 times px of 2 plus ... Actually, I'll write one more. I'll go one more. Plus 3 times px of 3 plus ... forever. And that will go all the way towards infinity, or it could stop at some point in time. I'm now going to cleverly rewrite this summation at the top here. And then what I'm going to do is, wherever I see a multiple of a probability, right? So 2 times a probability, 3 times a probability, I'm actually going to rewrite it in the following way. So px of 2, I'm going to split it up into its px of 2 and px of 2. Px of 3, I'm going to split it up into its component roots, and don't forget that I've still got the px of 1 here. And basically, I'm adding them all together, right? If I go back, I'm still adding them all together. I'm just splitting them out in this way so that we recognize, or that we can do. All right. Now we're cooking with some level of gas. Because now that I've split it out in this way, I want you to notice the following pattern. This first summation here is the probability x equals 1 plus the probability x equals 2 plus the probability of x equals 3, and so on. So that first probability there happens to be equal to the probability that x is greater than or equal to 1. That very first probability, again, because I'm going 1 plus 2 plus the probability of 2 plus the probability of 3 plus probability all the way to infinity. The next probability, you'll notice now, is I don't start at 1, but I start at 2. So the probability of x equals 2 plus the probability of x equals 3 plus all the way in forward. That is the probability that x is greater than or equal to 2. Plus the next term, what do you notice? You've got the probability x is equal to 3 plus probability x equals 4, so on and so forth. That is the probability that x is greater than or equal to 4. Greater than or equal to 3. And then that can continue onwards. Now, alternatively, we can rewrite the first, in fact, not just the first term, but all of these terms in the opposite way. And what do I mean by the opposite way? Well, that is 1 minus the probability x is less than 1. In other words, I'm rewriting it with respect to the complement event. So notice, when you have the idea of, as an aside, if we have the probability of A plus the probability of A complement, we know by our probability that the sum of an event and its complement must be equal to 1. Or in other words, we can rewrite this and say that really the probability of A complement is equal to 1 minus the probability of A, or alternatively, the probability of A is equal to 1 minus the probability of A complement. So in the example above that I just went through here is our event, say A, x, the event that x is greater than or equal to 1. The complement of that event is x is less than 1. And so using this formula here, that probability of A is 1 minus the complement, probability of the complement, that's what we have in the term below. Similarly, we can do the same thing for the second term. We can rewrite this as 1 minus the probability that x is less than 2 plus, and then so on and so forth with the other terms. Then what I want us to notice is that the probability x is less than 1, again, because x just takes discrete values, this is simply the same as the probability that x is less than or equal to 0, right? Because we know it's less than 1, can't equal 1, so therefore we can go to the next positive integer down, or the next integer down, and we can say we can include that integer in the inequality, but we can include it, and we can now say it's less than or equal to. Same thing for the next term here, 1 minus. The probability that x is less than 2 is the same as the probability that x is less than or equal to 1, because it's the next integer down. Plus, and if we were to go in the next part down, we could actually rewrite this as PR of x less than or equal to 2. And this pattern would continue onwards forever, in fact. Hopefully you can see that. And finally, after all of that huffing and puffing through this, we can rewrite this as 1 minus fx of 0 plus 1 minus fx of 1, because that is the definition of the cumulative distribution function, plus 1 minus fx of 2, plus dot, 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 dot. And if we wanted to put this in summation notation, we could say that's 1 minus fx of x from x is equal to 0 to infinity. And there, ladies and gentlemen, I have also proved another important result. That's saying that when x is a non-negative integer discrete random variable, in other words, it takes, recall, it took that my assumption here was that x takes the value 0, 1, 2, 3, and so forth, then I can rewrite the expected value in this form. So let's have a look at an example. Or an example 2, I should say. Let x represent the number of defective items in a batch size of 3. With, and let's say the probability mass function is given by the following. X, probability X is equal to X. Say it takes the values 0, 1, 2, and 3. And it takes those with values 0 0.3, 0 0.4, 0 0.2, and 0 0.1. Let's suppose this is our probability distribution function or probability mass function. And now our goal here is to find the expected value of x using the CDF or using the cumulative distribution function. So let's do that. The first thing to do here in this particular example is to actually calculate the distribution function for each of them. So, for example, fx of 0, which is the same as the probability x is less than or equal to 0. This is just simply equal to the probability x equals 0 is 0.3. Fx of 1, which by definition is the probability x is less than or equal to 1, is equal to the probability that x equals 0 plus the probability x equals 1, which in this case has to be 0.3 plus 0.4, which is 0.7. Fx of 2, which is by definition the probability that x is less than or equal to 2, is the probability that x equals 0 plus the probability x equals 1 plus the probability x equals 2, which is equal to, in this particular instance, 0.3 plus 0.4 plus 0.2, which is equal to 0.9. And finally, in this final calculation here, fx of 3 is equal to probability that x is less than or equal to 3, which is the probability x equals 0 plus probability x equals 1 plus probability x equals 2 plus probability x equals 3, which is 0.3, 0.4 plus 0.2 plus 0.1, which is, going back here, simply equal to 1. And so if we were to rewrite this distribution function, which I will do here, copy that, and we could say paste it here. We could paste it here. We can put this in tabular form now. And I will just say here, we can rewrite fx of x now. We can add it to the table. It's 0.3, 0.7, 0.9, and 1. Keeping that in mind, we can now calculate the expected value. So using the cumulative distribution function, the expected value is, recall, x equals 0 to infinity of x times, that is the old definition. Here is a computationally unique definition. 1 minus fx of x, which in this particular case, now, in the definition that I gave above, we went all the way to infinity. Which is true because technically, if we were to extend this distribution, right? Let's say just hypothetically, we were to extend this, 4, 5, 6, and, so on and so forth. Each of these has a probability of 0. And the cumulative distribution, right? So for example, the probability that x is less than or equal to 4, well, that's just still equal to 1, right? Because it covers all your bases. In fact, it's 1 for all of these particular cases, 4, 5, and 6. Again, because the probability x is less than or equal to 4, or less than or equal to 5, or less than or equal to 6, well, that covers all the cases of 0, 1, 2, 3, and 4, so it'll sum to 1. What does this mean? Well, if you look at all these cases above, particularly where x is greater than or equal to, or greater than 3, 1 minus the cumulative distribution function, right? 1 minus, in this case, 1, 1, 1, 1, 1, 1, 1, is just simply 0. And so I don't need to worry about those cases. I can simply just go up to the maximum value of x in our distribution, which is 3. Because once I go to 4, 1 minus the cumulative distribution function is just 0. So anything beyond the maximum value here of 3 is 0, and we don't have to worry. So that definition can actually be, or that last terminal can be altered. This gives us x equal, now substituting, I guess, our values that we have. This gives us 1 minus fx of 0 plus 1 minus fx of 1 plus 1 minus fx of 2 plus 1 minus fx of 3 in our definition here. And I've just accidentally lost the page a little bit. So putting that down now, this gives us 1 minus, in this case, 0.3 plus 1 minus 0.7 plus 1 minus 0.9 plus 1 minus 1, substituting in the values that we had above, which is equal to 1.1. And so there you have it. Here is another case of using the or finding the expected value of a random variable using the CDF. I hope going through this example, or this first example and second example, were useful. Thank you for watching. Hope to see you in the next video.